So I will talk about quantum advantage and how we define it, how do we measure it, how do we hunt for it in theory and in practice. And yeah, so my current title is slightly different, but at heart I'm still a senior research scientist like before. My current title is Product Development and AI Strategy, which reflects a bit more what I was doing in the last 2 years in Quantinuum. So Quantinuum, for those who don't know from the audience, is the biggest standalone pure play quantum computing company with lots of scientists and engineers in many different countries. The hardware is based in the US, and the software and algorithms teams mostly in the UK, but we have also other offices that are doing heavy algorithm work in Tokyo, in Munich, also in the US, in Colorado, in Broomfield. And in the UK is where I am based. I'm based in London. And I'm mostly focusing on quantum algorithms for problems that theory tells us there should be quantum advantage. And also I'm integrating AI and quantum together to see how we can write better quantum algorithms, for example. But I think this is a story for another day. Today we'll focus on quantum advantage. So um, I'm working by having in mind the full stack of Quantinuum. The new quantum stack includes high-level programming languages like Guppy, for example, which is a very Pythonic language, which allows you to write quantum algorithms. So I think it's very useful for people getting into quantum to start from there, because it's one thing to write quantum algorithms in a language where you're familiar with the logic, right? Because it's just standard, it's similar to just standard Python, instead of something more low level, like Ticket, which is at the circuit level. You get to play with gates directly, but that's also useful. I mean, sometimes it's useful to get down into that level when you want to really optimize things, which is something I will talk about. And then at the bottom we have the hardware, of course, and the hardware, as Yanis also mentioned. Um, yeah, we have a lot of partners. I'm going to skip over this, but the hardware basically is very exciting because, as Yanis mentioned, we just announced Helios. It's a new machine. It has 98 qubits, and importantly, they're fully connected because the qubits on our chips, they're ions, and they're sitting on their own individual traps. Each qubit has a trap, and they're driving their traps around like cars on a highway. And basically, if you want to gate them, and the gate fidelities are the highest on the planet on commercially accessible quantum computers. If you want to gate them, you take your 2 qubits and you park them on the gate zone, and then you shoot them with lasers. And then a quantum circuit basically goes through a compiler, and the compiler has to interpret it and organize a dance of ions, of moving them around, sorting them, shooting them with lasers, moving them around again in sequence. It's a problem which is in general hard to organize this, but in practice we have very good heuristics to do this. And the the hardware roadmap is looking towards the end of the decade, where we are predicting that after Helios, we will have these chips that can fit even more qubits, which allows for encoding even more logical qubits and so on, which also allows more complex quantum algorithms. And I will show you how this timeline is relevant for the use cases I will talk about in detail later. It's good to have this in mind because also it informs what type of quantum advantage to hunt for. So because quantum computing is at an early stage, however impressive it is today, it's more beneficial to hunt for quantum advantage, which is promised to be exponential rather than quadratic or low polynomial. This is because exponentials kick in very, very fast, so you can get the most and squeeze the most performance out of your quantum computer. This is what I mean by this comment. Okay, what do we do with these quantum computers? what algorithms do we run on them, and how do we make them useful. This is the whole point of quantum computing at the algorithms and application level. And I want to point out that advantage comes in many different flavors. It's not just a generic thing that you get or don't get, right? It's not something that you have one day and you don't have another day and so on. It's something that is depending on the problem and even more specifically on a problem instance, as we will see later. And it's not something that you can get naively, which is sometimes a misconception that we find in the industry or in early academia, where basically there is the misconception that quantum computers can do in superposition some computations. Therefore, then I have exponential advantage automatically. It's not how it works, because then you have to measure, right? And you get some output with some probability, and then you have to restart. Also, not any generic machine learning application can be sped up with a quantum subroutine. It also depends on the structure of the problem. So identifying quantum advantages, it's quite fine and delicate, and I will show you in detail how you get it or how you estimate where it is for a specific problem. But first, I'll give you like a very, very fast tasting menu of quantum advantage flavors that have appeared in the wild, and specifically that we have published from Quantinuum. So one flavor of advantage, one dish, is sampling. So sampling means I can sample from a distribution using a quantum computer more efficiently than I can sample or simulate sampling from classically. An example is the very famous random circuit sampling experiments. The first ones to introduce this were Google in 2019, as everyone knows. So the version that we have run actually, which is still to be simulated by anyone, is using a generic topologies. So basically what you do is not only you randomize the gates on a quantum circuit, as the first proposal from Google was, it was also, what we did was also to randomize the connectivity between them. So this is enabled by the fact that, as I said before, any qubit can be connected with any other qubit because we can physically move the ions around. Whereas on other chips with fixed topology, which is usually the case with superconducting chips or silicon chips or integrated photonic chips, what you have is a fixed topology, and then you just sample random circuits which are constrained by that. Whereas here, I repeat, we are sampling random configurations of circuits. So random circuit sampling is exactly this. You run basically random programs, you don't know for which you have advantage, and you say, I'm going to run all of them. And you randomly sample gates, you put them in a row, and then you make sure that it's very dense, the circuit, so you cannot simulate it classically because there's too much entanglement getting built up. And then you just sample the outputs. The outputs are just obtained by measuring all the qubits. At the end, you get an output with some probability distribution, and sampling from that distribution is hard to do classically. Therefore, quantum advantage if you do it at a large enough scale, which is something that we have done a couple of years ago and published. Another version of this is complement sampling, which is very interesting. It's a problem which is as follows. Someone gives you a set of bit strings. You can create their superposition in a state, S, and then the task is sample from the other ones. The other ones are all the other bit strings of the same length that are not in this set that someone gave you. This can be done with only one shot on a quantum computer. The algorithm that enables this, I will not get into details. You can look at this paper here. I don't want to focus on this too much, but it's a second flavor of sampling advantage because it's not based on random circuits, and it's a bit more tangible. This is enabled by the fact that quantumly you can swap this superposition of S that someone gives you with the superposition of the other bit strings that are not in that set. There is a swapper circuit that enables that. And if the circuit is noiseless, if the gates are perfect, then you can do it with one shot, like with probability of success 100% probability. You can take one sample from your state because you have swapped it and you've measured from the other set. Classically, you need to try exponentially many choices. So this is like maximal advantage. And these things also have weird applications that were not predicted in the beginning. Like these sampling-based advantage experiments, they were seen as useless in the beginning. Just like their point was just to get advantage computationally, and there was no application in sight. But after thinking very, very hard, people came up with um, ways to apply these random circuit or complement sampling experiments to cybersecurity applications. Basically, it's about creating randomness that is certifiable and verifiable quantum. So you can promise to someone, I'm going to give you a random number, and it was generated by a quantum process. So it's proper random from mama nature, instead of pseudo-random, which is something simulated with complicated classical circuits. And I can prove to you with minimal assumptions that it was actually a quantum computer that gave it to me, and I'm not cheating here. Now, what I want to focus on this talk is this other flavor, like the main dish is computational advantage. So quantum computers follow this slogan when it comes to computational advantage. The slogan is small data and big compute. So this means that your problem has an efficient classical description. So it's very easy to describe the problem to someone, but nevertheless, it requires a lot of compute to be done. And this computation happens to be done efficiently quantumly, but no one knows how to do it classically efficiently. So it takes exponential time classically most of the time, and polynomial time quantumly, which means not that much in computer science jargon. So I will focus on this case study, which was a recent work that I led and we published from Quantinuum with a lot of co-authors. Brilliant people. I urge you to look at this paper. So this is about a case study of a problem that has a long history in quantum computer science. Even though it's a weird problem that comes from mathematics, it's very interesting to quantum computer science because it is complete for a quantum class, which I will tell you what it means in a bit. But first, what is this problem? This problem is about computing these things called knot invariants. Knots are these squiggles, so literally like knots that you tie your shoelaces with, but the only difference is that they only have closed ends. There's no open ends on these knots. They're just closed loops, but they're kind of tangled and knotted together. This is the simplest knot you can make. It's the trefoil knot. And these are 4 different ways to draw it. It's the same object, literally the same topological object. It's the same knot, but I've drawn it differently. So knot theorists, they have huge tables of knots, very complicated knots, and they want to classify them. When are they different? When are they the same? So the idea is if 2 of them have a different property, some mathematical property, then you know that they are different knots. One of these things, one of these invariants is this Jones polynomial. It's a polynomial in one variable, and its property is that it is invariant under deformations of the knot. So because these are all the same drawings of the same knot, then this thing doesn't change. This is the point. If for another knot, this is a different polynomial, then you know that these knots are topologically not equivalent. So they're different. And what we want to focus on for a quantum algorithm is actually evaluating such polynomials at a point. So we'll tell you how this works in a bit. First of all, I'm going to give you an intuition for why this is hard classically. So classically, what you have to do to get this polynomial is someone gives you this knot, this trefoil knot, and you have to resolve it. You have to break every crossing as 2 avoided crossings, one vertical, one horizontal. And every loop that you have costs some factor, this factor here. Now, if you do this, you see you have 3 crossings here. And if you resolve all of them, you get 8 terms. This is because you have 2 terms per crossing, and we have 3 crossings. So 2 to the 3 is 8. I have 8 terms to sum. And if I sum them over, I get this. This process is called the Kaufman bracket, because Kaufman introduced it and he called it the bracket. And then if you add some prefactors, which I'm not going to get into, but they're easy to get, and you multiply the Kaufman bracket and you change some variables. Again, I'm not going to get into this. Kaufman's book is brilliant. You should all read it. You just get the Jones polynomial after you do all of this. Bottom line, you just have to do an exponentially big sum. You see, it's an exponentially big sum because it's always 2 to the number of crossings. So a knot with 10 crossings would have 2 to the 10, right? So 1024 terms to sum over, and then it grows exponentially after that, which is very difficult to do classically, right? Exponentially big sums is a problem. But quantumly, it just happens that if you want to evaluate the Jones polynomial at a very specific point, basically any point on the unit circle. So if this variable of the polynomial is some phase, some complex phase, there is a quantum algorithm that can do it in polynomial time. And what I meant before by completeness is that any quantum algorithm of this class is called DQC1, that is defined by this problem. This class contains all of the quantum algorithms that are equivalent to it in power. So what does this mean? For every completeness means that for any other quantum algorithm of the same computational class, there exists a knot or a link or a closed braid, as I show here, for which evaluating the Jones polynomial is equivalent to solving that problem. Okay, why is this important? Why was this relevant in the history of quantum computer science? Is because it is believed that these quantum classes, these complexity classes, are beyond classical. So if someone knew how to do this problem classically efficiently, then quantum would be the same as classical, and there would be no point in quantum computation at all. So we don't believe this is the case. Of course, there is no proof in theory. There's many open conjectures in complexity, but we don't believe that this is the case. We do not believe that quantum equals classical. We believe that quantum computers have more power than classical computers in general. And so this problem is a good candidate for quantum advantage, evaluating the Jones polynomial at this fifth root of unity, this point here. Now, specifically, I've drawn this complicated object here. Why? Because any random link that or not that someone draws for me, I can draw it as a closure like this of a braid. A braid is a sequence of these swap operators, these swaps, these braid generators that I've put on this blue box. And evaluating the Jones or estimating the Jones polynomial value of this object here for a given braid is efficiently done on a quantum computer. And what you do is you basically estimate it at this additive error here. Phi is just a number. It's a golden ratio. It's 1.6 something. But the point here is that you know what this error is. You know what the braid is. You close it. And then you know that you need to get these many shots on a quantum computer to estimate it to this error. And there is no classical algorithm to do this efficiently. I repeat, this is important. The quantum algorithm looks like this. I will not get into all of its details, but I'm going to describe to you how it works. So how it works is as follows. Every one of these crossings, these braid generators, someone gives you this braid, this blue braid. Every one of these braid generators has a circuit corresponding to it. This is because the algebra that is obeyed by these braid generators has a unitary representation. Basically, what this means is that you can encode it efficiently in quantum circuits, and this is what is done here. Someone gives me a braid, I can get its braid unitary. I can get a huge unitary that describes the whole braid, and there is an efficient way to compile it into circuits. I just compile its generator, and then I Lego them together as dictated by the braid structure. Now this, in the pink box here, I'm showing the Hadamard test, the vanilla version, the basic version. The Hadamard test is a quantum protocol which allows you to estimate the trace of a unitary matrix. Unitary matrices are exponentially big. So, and we know that the trace of a matrix is basically a sum over its diagonal, right? So what we're talking about now is an exponentially big sum. there is a quantum protocol that can do this for you. It's the Hadamard test. Basically, you have this ancilla qubit here that controls your unitary. It's initialized in the plus state. And then this S here is a bit string that is sampled classically. Every time you sample one of these bit strings, you run the circuit, and then you measure the first qubit. And then you sample another bit strings, and then you measure again. If you do this many times, from the probability of measuring 0 on the first qubit, you can get the trace of this unitary estimated. And you see you're estimating this sum because you're sampling over the diagonal by every time sampling a different bit string on this S. And then choosing to do or not do this S dagger gate here allows you to estimate the real and imaginary part of this trace. Remember, this is a complex number we're trying to estimate because the unitaries are complex valued, and its trace in general is a complex number. So it's a very simple protocol. You just have to do a control over your unitary and measure the first qubit. It's kind of trivial. Here we pimp it up. Basically, we add some tricks. The unitary goes here. You see we have removed the control by using this trick with the cut state preparation circuit that is depicted here. It depends on the bit string that we are sampling, but it's nothing crazy. And then we're also using some error detection tricks. So basically, we check whether the input state here, these S strings that are being sampled to estimate the trace, we check if the input comes out. If it doesn't come out, it means that some error happened. We don't know where, we cannot correct it, but we know that that shot was garbage, we can discard it. So at the cost of more shots, we can get better accuracy, so less variance on our estimate of the trace. Again, I just have to measure the first qubit, and the other qubits are measured only for this error detection trick. Now, if no one was paying attention in any of this because it's too much, the only thing you have to keep in mind is that given one of these braids, there is a quantum algorithm that can do the trace estimation of these unitaries that represent the braid, and you only need some number of shots, capital N, to estimate the trace with 1 over square root of n Monte Carlo error, right? So there is a quantum algorithm to get the trace, which is the answer to the problem. Because the trace goes here, and then there's some prefactors, and then you get a Jones polynomial. That is the point here. You can do trace estimation efficiently. And computing the Jones is just a big sum, which is the trace. There is a question in the chat. No, there is no question. So let's continue. This is just a demo of how you run this quantum algorithm on a quantum computer, an actual quantum computer, the H2 machine. This is the one previous to Helios, which was just announced this week, but it's still a powerful quantum computer. It had 56 qubits, but here we only used 16. And we just ran this big braid. And I can show you that basically in the beginning, the quantum algorithm estimated the Jones on the complex plane to be here, this number, the orange star. And then if you do your extra error detection and error mitigation tricks that we have invented for this algorithm, you can get closer to the actual value. The actual value is the purple one, and the true value is the blue one. So if the gates were perfect, there was no error on the gates, we would just get the blue one with some fuzzy cloud around it, which is because we're getting shots to estimate the trace. Now, at the same time, I'm talking about quantum advantage, right? So what I'm talking about is not only how the quantum algorithm is operating, but also how the classical algorithms are competing. Because quantum advantage is to be compared against the classical best algorithms for the same problem, right? Not just the naive ones, but the best ones. So what you have to do is also improve on the classical algorithms. And we did. We introduced this tensor network-based algorithm that I'm not going to get into it in detail because we describe it in the paper, and this is a high-level presentation. But the juice is you get the braid unitary, and you compress it with this tensor network technology called matrix product operator. You compress it, and then you do your trace with tensor contraction. So instead of doing it on a quantum computer, you can do it on a GPU by using tensor network methods. And then what you can do is you can check how accurate it is. So if your compression starts becoming lossy, so you're introducing errors effectively, morally similar to how gates on the quantum computer have errors, you can measure the effect of that to the accuracy of the result. You can also measure how many flops it takes, how many floating point operations it takes to get that result. And you can extrapolate by system size, by how big the braid or link is or not. And then you can see how long it would take on a classical computer, assuming it is running on one GPU for 1 month, or on the biggest quantum supercomputer, Frontier, for example, for 1 month, and so on and so on. So how many floating point operations do you need? So this is characterizing the classical algorithm. Then you put everything together by running a benchmark. A benchmark, the point of the benchmark is to compare how the noise affects the result on a quantum computer and how big a classical computer can get, right? So this problem is very specific. It has this hidden structure of invariance. As I told you, if you compute the Jones for some representation of the knot, some drawing of it, and if you draw it differently, but you know it's the same object, the answer should not change. So what we do is we augment some given braid for which we have the answer, we know it already, and then we augment it to look bigger than it is by adding a lot of crossings in a way that it doesn't change the topology, so the answer should not change. But now more gates are affecting the answer because of noise, so we can characterize it. And if we assume in simulation now, not on an actual quantum computer, if you assume two different error models, so if per gate the error is of this, it's 5 times 10 to the minus 4 or 1 times 10 to the minus 4, it makes a big difference. So you see the drift from the actual answer is either like close to 100%, so total garbage to the output, versus only 20% error for braids of size 1,500 crossings. So we see that gate noise on the quantum computer makes a big difference. So slight improvements make a big difference. And then if you put everything together, like how long it takes to get to the solution, given classical or quantum hardware and the state of the art classical and quantum algorithms, respectively, you can put everything together and you can say, I assume that the classical computer has this, the quantum computer has this error in the gates. You will see you have no advantage because in the beginning, the classical algorithm tries to catch up. It has an exponential cost. This is a log scale, so it grows up. The time to solution grows, and then it drops because the quantum computer now is outputting garbage because the problems are too big and the errors are too high. So the classical algorithm has a easy time to output also garbage. But if the fidelity on the quantum computer is very high, so if the errors per gate are low, it's this orange data that we have plotted here, then you see that the time to solution on a classical computer, say on a supercomputer here, you see it starts crossing this boundary. And this boundary is the quantum computer running for a week. So when you have this crossing, the crossover, where the time to solution on the quantum is less than the classical, then you say, I have advantage. This is the advantage crossover point. But the methodology stands even if someone improves the quantum or classical algorithms, right? It just shifts the advantage point somewhere. But theory tells us that advantage should exist somewhere, unless someone makes a breakthrough in quantum complexity theory, but then everyone should just stop doing quantum computation. But this is not the case. So in short, quantum advantage here in the computational problem is, can I compute this quantity faster on this device or this device, given the best classical or quantum algorithms? It's not more complicated than that. It's actually very, very simple. What is complicated is doing this properly and estimating and evaluating all of these errors, how they propagate, and estimating the time to solution given those errors, given some hardware and given behavior of a classical and quantum algorithm. So that was it for this problem. I'm going to give you an example of quantum dynamics, which is another example of a problem with small data and big compute. I'm just going to flash this. Um, I'm, um, I'm redirecting you to this paper here. Basically, the small data here is the Hamiltonian that describes a many-body system. And the big compute you have to do is basically multiply together exponentially large matrices. These exponentially large matrices describe the evolution of the quantum state from one time step to the next time step. And for long time evolutions, this starts becoming classically hard. Again, for a similar reason as to why random circuit sampling is hard. The reason is there's too much entanglement getting built up, and the entanglement is getting built up by a universal gate set of quantum computations. So there is no other way to do this classically other than use a quantum computer. What one wants to measure here, however, in comparison with, in contrast with random circuit sampling, is that whereas in random circuit sampling, what you're doing is measuring just all the qubits and getting the whole bit string output and seeing its distribution. Here we're measuring actually physically relevant quantities. So 2-point correlation functions, which are local operators. And by the way, local operators behave very nicely against errors. So anyone interested in physics, they have an advantage here. I mean, a research advantage, because the quantum computers of the next 5 years are particularly suited to condensed matter many-body physics for the reason that the dynamics are generated by local Hamiltonians and errors don't impact them as hard. For example, for the Jones polynomial, this not theoretic problem we just talked about before, the errors actually do impact it much more because we are obtaining topological information from the whole circuit. Whereas here we're only measuring some local qubits, and the rest qubits, we don't care what they do. So here we are seeing basically that the quantum computer, which is the purple lines, are tracking the time evolution of these local observables like correlation functions, local correlation functions, or local density of magnetization or something like this. This was for an Ising model. The Hamiltonian is up here. It's basically spin-spin interactions on a grid or on a graph dictated by whatever topology has been chosen by the Hamiltonian, plus some local magnetic fields. And then the time evolution is driven by this Hamiltonian. And what you're seeing here is the expectation value of Z square, which is the local magnetization, is tracked by the quantum computer much more accurately than any other classical method tried, from neural quantum states to matrix product states. Any other classical method is just going off track, is losing the time evolution. It cannot keep up because there's too much entanglement getting built up. So this is a demonstration of quantum advantage for quantum dynamics in a regime where the correlations are so strong that classical cannot keep up. So quantum advantage here appears again as a time to solution. Like if you wanted the classical algorithms to match, you will need to spend exponential time or exponential RAM or both to achieve the same fidelity to the number, to this magnetization, as the quantum computer is getting in just polynomial time. Other examples of this slogan of small data, big compute are quantum chemistry, where quantum chemistry, again, the problem is, here's a Hamiltonian. It describes a lot of electrons on many different orbitals, occupying orbitals on a complicated molecule. So it's a very long range, non-local Hamiltonian describing a lot of interacting electrons. And as we know, the Hilbert space grows exponentially. So if you want to find the ground state of this Hamiltonian, classically what you have to do is either use tensor networks and heuristics, or simply deal with diagonalizing an exponentially big matrix. So again, exponentials come in, and the quantum algorithm for this task is called quantum phase estimation. I will not get into this today, but it's a very famous algorithm. It allows you to estimate the ground state energy, i.e. the smallest eigenvalue of this Hamiltonian matrix, which is an exponentially big matrix, I repeat, as long as you have a very good initial state. So the small data is the initial state preparation circuit and the Hamiltonian, and the big compute you have to do is diagonalizing this big matrix, which with quantum phase estimation you can do on a quantum computer. Another example is QTDA, quantum topological data analysis. Here, you are given a graph and you want to extract some features of this graph, some topological global features. Basically, you want to check how many holds there are of various dimensions, specifically percentages of holds. That's what these are, the so-called normalized Betti numbers. What is happening here is, again, this problem reduces to estimating the trace of a big matrix, exponentially big matrix, which is extracted from the graph. So the small data here is the graph. It's easy to describe a graph to someone, but getting the trace of an exponentially big matrix that is defined by the graph is a hard computational problem. And again, similar to the Jones polynomial case, there is an algorithm to do the trace estimation on a quantum computer. This is an interesting algorithm, actually, because it has many applications that the not theoretic one doesn't, because you can actually run this on any random graph someone gives you. Namely, this graph is describing how some proteins are talking to each other on a omics, multi-omics network. Or it could describe some point cloud data set of users on the internet. It can be literally applied to any point cloud data from which you extract a graph or a graph that someone gives you. Basically, it's feature extraction. It's a way to get quantum data or quantumly obtained data from classically big data. And then there's other examples like differential equation, time evolution, which you reduce to quantum dynamics, like in the case we described before. There is optimization, which is a very classic example from the 90s, where basically you have to search over combinatorially large space of possible solutions and so on and so on. But the slogan is the same always: small data, big compute. If you don't have this, computational quantum advantage is probably not going to be there, unless you get very, very lucky with heuristics. And now, since I am mentioning heuristics and getting lucky, I'm going to close with this. This is the strategy, AI strategy that we are following in Quantinuum. Basically, there's two parts. There's a part where a classical AI is solving quantum problems, so like compiling circuits, writing new quantum algorithms, etc. But the second part is about obtaining quantum data, like I just discussed, for example, from TDA, and supplementing it to existing classical data sets, and then using that extra quantum data to train other AI systems for some downstream scientific discovery tasks, like material discovery or drug design or something like this. But I don't want to focus on this big overview. What I want to focus on is this idea of quantum easy instances, or equivalently, problem instances for which we have quantum advantage in terms of time to solution, like I outlined in the Jones polynomial or quantum dynamics use cases. What does this mean? We are shifting our thinking about quantum advantage in the following sense. We are not thinking of quantum advantage for problems. We are thinking about quantum advantage for problem instances, right? Because there might be some instances of a problem which are actually easy, both for quantum and classical. Some instances of some problem could be hard for both quantum and classical. Where you have advantage is for instances of a problem where you have your answer fast on a quantum computer and hard on a classical computer. I know this sounds like repetition from before, But the focus on instances is important because, for example, in the knot theory case, let me go back to that slide. In the knot theory case, if you see here on the x-axis, I've only shown you the problem sizes for which I have advantage, but I didn't tell you exactly which knot or which braid. To find exactly some specific braid of that size, 2,800 crossings or 3,000 crossings, for which the quantum algorithm is faster than the classical, is non-trivial. It's non-trivial for many subtle reasons. One subtle reason is, for example, the way we constructed our benchmark grades here is such that we knew the answer already. We knew the answer was some number for the Jones polynomial. And then we augmented with complex, highly connected braids on either side, such that we don't change the answer. Okay. However, if I don't know the answer already, right? If I don't know the answer already, so that there is even a point to talk about advantage, and I also try to make it hard for classical naively, I would just choose a random, highly connected braid and say, it's big enough, you should have advantage for this because it's around the size for which you're predicting advantage for the benchmark, with the benchmark. But it's not that simple because if you take a random braid of that size, very highly connected, etc., you will find that with a very high probability, the Jones will be zero. Like the answer is easily predictable. This is because all amplitudes in random braids are like amplitudes in random circuits, because braids are also universal for quantum computation, and so on. And so the idea is that all amplitudes are more or less the same amplitude in magnitude, exponentially small, of course. And this results in the Jones polynomial being very, very close to zero. So a classical spoofer can just predict zero. Predicting zero will spoof it. So again, the advantage gets destroyed. So the proposal here, this flowchart, is about searching for these quantum easy instances methodically. You are using as oracles or resource estimators these quantum computers and classical computers and their quantum algorithms and classical algorithms. And also, the resource estimators are informed by them so that they can tell you, here is an instance. Do you think there is advantage for this? If yes, you're happy. But if no, you have to propose a new instance. And this iterative modification of a new instance is basically what fancy search algorithms that are constructing objects that have some specific property, right? It's phrased as a single player game or a search problem. This is what you use AI for in many other applications in mathematics or engineering. Here, the idea is to apply this for searching for these queasy instances or quantum easy instances. And this is something we are working on in Quantinuum. And I will close by showing you that we have a recent paper on formalizing this. It's a formal framework for quantum advantage where we are defining with a lot of math from Kolmogorov complexity style definitions. We are defining what quantum easy means. We are defining instance complexity and quantum instance complexity as the as the size of the description of the shortest program that can solve that instance, right? And then this is in bits. So the difference in bits of these descriptions is basically the queasiness. And then we prove that by reduction from factoring that there are infinitely many queasy instances. And so all you have to do is find them. So finding them in practice needs, it requires a lot of these computational and numerical tools that I talked about before, maybe with the help of some AI. But these are the theoretical foundations that promise you that if you look hard enough, they exist, they're out there. And with this, I will close.
Thank you, Konstantinos. Yeah, we have at least one question. Maybe it even contains multiple by Irina. I also added one, but let's start with the one from Irina. Hi, Konstantinos. Please advise how the provided examples can be applied, for example, for the supply chain scenario simulation and optimization when we add additional complexity / increased metrics parameters by introducing circular economy / sustainability, profitability, and some other parameters. And the goal is to find the optimum nexus point. That's the first part of the question.
It's a complicated question.
I can also unmute Irina if that would help.
Okay, let's see. Supply chain scenario simulation optimization when we add additional complexity, increase matrix parameters. Yeah, I think you have to start by isolating a problem first. If you consider everything together, you cannot really separate the contribution of the quantum subroutine. So if you focus on a problem in kind of a sandboxed way, like if you have some subroutine which you know what job you should be doing, it's easier to quantify that. Like if you have somewhere in some complicated workflow, say in optimization, some optimizer, and you know what it should be doing, and if you replace it with some quantum solution, then you just quantify it against what that thing should be doing, right? If you don't know all the secondary effects of the whole chain, I think the only way around this is just swapping in the quantum solution and checking the output end to end, right? I mean, the quantum algorithms I showed were designed to work end to end. There's a well-defined goal: compute the Jones polynomial, compute me these correlators versus time, and so on and so on. In the real world, the outputs are not so easily evaluated, right? Maybe the effect is secondary. Maybe the effect is more long term. So I don't know really how to answer this um, other than if you have concrete metrics, then you don't have a problem. You don't even need to ask the question. If you don't have concrete metrics, then you just have to try it and see it heuristically. But then you have to evaluate the cost of actually changing your whole supply, right? So you better have a digital twin or emulator of your whole supply chain with proxies for what's happening. But if you want to have this, then you need to have some metrics, right? So we're back at square one. Does this cover, Irina?
Yeah, thank you, Konstantinos. Yeah, just what my idea was, because in examples that we read, it's supply chain optimization. It's already the task that the computer, quantum computing, is helping, and so we know it's possible. But what is the difference in our particular use case? We would like to introduce an additional parameters at the minute they're running separately in the same, I would say, platform solution, powered, quantum powered. So then, like, yeah, it's all possible scenarios. Once you change one of them, it's influence the remaining four, for example, or five. And the same, it's then you can get a data and actor. I mean, of course, I understand there should be like almost initial metrics parameters describing through value chain, describing each of these aspects. My question was how to actually to run them all simultaneously, because metrics quite be actually, as you mentioned, exponentially grow. So, and how for us even to would be the first stage, if for example you would be that person who could help us to implement the AI plus quantum, what kind of information we need to provide? Do we need to create some kind of spider map with all the possible data, how they connected to make it happen?
So we're talking about combinatorial optimization problems, correct?
Yeah, to find this. Yeah.
So currently, the approaches that are used for these combinatorial optimization problems are in the style of QAOA or annealing-inspired scheduled QAOA and so on. And a variant of that, a more modern variant, would be you have some language model that can, which is tasked to write good circuits, which prepare states which are superpositions of the solution space, or at least as close as possible to that. This would be the AI for quantum optimization angle. But all of these are evaluated in an isolated setting where you can quantify the performance of the optimizer. So for example, you want to look at approximation ratio, right? It's a quantity, and then everyone can benchmark against that. If you don't have that well defined, you don't know if the quantum is helping at all. That's all I'm saying. So depends on the problem, of course, but if you don't have well-defined metrics for your success, then you can use whatever you want as long as it works. Now, one thing to consider, of course, is quantum computing is not to be used real time very fast because there's not that many of them around. They're slow in clock rate, so the advantage appears when you have exponential advantage, right? As you saw, my crossover appears at problems for this Jones polynomial, for example, appears at very large problem sizes, thousands of crossings in my braid. And it appears if the quantum computer is running around 1 week, 1 week of runtime, right? And then the classical supercomputer now needs years or something. But you will not see the advantage in like seconds versus milliseconds or something, with the exception of the sampling problems. Like in sampling problems, the quantum computer runs order of seconds, and the supercomputer is running, hours or weeks. So it depends also on the application. Optimization is not a sampling problem. You are sampling solutions, but after you have done a lot of annoying, slow work. So one approach to thinking about quantum and optimization is make sure you are targeting a problem which is reusable, right? It's not to solve one problem once and then be done with it. It's for some problem that is so important to be solved that you can also try quantum to see if it helps for optimization. And I say to try and see if it helps because optimization comes with no guarantees, right? It's heuristics. Unless you happen to be working with an optimization problem that happens to be one of those that arises from a reduction from another problem, like we reduce from factoring or something, from which Shor's algorithm exists. But generically, in the wild, most combinatorial optimization problems are just whatever, some random thing. So you just need to try heuristically. But for quantum to be worth it, it needs to be worth the waiting time and the resource cost for it. So it should be a problem that, whose solutions you need to sample a lot later. So I think this goes to your circular economy and sustainability also. Because at least currently, since error correction overheads are not insane yet, and even if they are, maybe you can just do FPGA for everything, so it's cheap. Quantum computers are more energy efficient than classical. So when you have exponential advantage in time, you also have exponential advantage in energy consumption, right? So if it's worth using the quantum computer for time to solution or quality of solution, it also happens to be worth it for energy reasons. But it's not always the case, right? Because if you want to do big data stuff, like if you want to do quantum machine learning, and you just need to use the quantum computer for years, okay, then probably it's hard to compare.
Yeah, thank you. It's really, really helpful. Thank you. Thank you, Konstantinos.
All right. I mean, I would have my question if we want to take this time. Konstantinos, would you mind bringing up this one slide? It's more of curiosity where you had your framework basically of AI proposing the solution and then checking whether this is quantumly hard.
Yes.
The search problem. I mean,
This
I'm
one?
just trying to understand. Yeah, it's I'm just trying to understand where there's still the complexity because the resource estimator basically means you need to have you already need, I mean, you need a mapping of your problem to a quantum circuit or something, right? To a quantum program. And
That's
finding
right.
that
That's right. Of course. So
also
here,
defines, yeah.
let's take the example of this again, this Jones polynomial thing, right? I have a clear target. I have a quantum algorithm that I believe is state of the art. I have a classical algorithm that I believe is state of the art. And I have assumptions for what quantum computer it is running on. So I know its fidelities and clock rate. And I have an assumption on what classical algorithm, sorry, a classical computer, the classical algorithm is working on, right? So is it one GPU? Is it a supercomputer? I should know, right? So these are all inputs to the resource estimator. Okay. The resource estimator then should be able to do automatically basically what I was describing here, right? It should locate this point. And it should tell you, for this instance that I chose that is of that size and so on, is my time to solution bigger or smaller on quantum or classical? If it's smaller on quantum, it should output advantage. If it's smaller on classical, it says no, find another instance, build another braid, right? So maybe this is a single player game where the job of the AI is to keep adding crossings until it builds a braid for which you have advantage, right? It's a search over braids, you see?
Yeah, exactly. And I guess my thinking in two directions. The one is more this, I guess it's even more statements. So it reminds me on, I don't know, my mother solving Sudokus from the newspaper, and there's just different difficulty levels, right?
Yeah.
Even if on the worst case Sudokus are hard. Well, I don't know what's the average case, but there can be simple Sudokus. Does this, and I mean, that's just the one thing, but does it also, or would this kind of open this bright future for quantum where you could see that this can basically be a check you want to run on many
Mhm.
problems? I mean, I don't assume this would happen in addition, but maybe you just say, well, I have my workflow here and I know how I can translate it in quantum, but I want to have it always as a backup. So before I run it on classical, I always will run it through this checker, and then I would decide on which classical or quantum I would schedule it.
Yeah. If you have a good resource estimation tool that could classify yes or no for advantage, yeah, of course. I mean, you can use it to search for new instances, as I am proposing here. But the reason I was proposing this is because I started from a generic notion where, I'm just sampling random instances to see the performance. If you have some instances you care about from some problem, having that resource estimation tool, of course, is a profiler. It tells you use a quantum computer for this, use a classical for this, and so on, right? Yeah, it's as simple as this. Of
Yeah.
course, it's easier to say than to do it, to build a good resource estimation tool. But it has to be done.
Yeah, yeah, right. No, this is interesting. I mean, I don't want to take too much time, but maybe last thought. I mean, we had this with generative adversarial networks. I'm wondering if we can build these
Yeah.
tools, resource in both ways, basically.
Yes,
That
yes,
would be also
absolutely.
interesting, right?
It is an adversarial setup. I mean, there's two adversarial setups, one on top of each other. One is for a given instance, the classical and the quantum are competing with each other, and they're trying to set where the advantage boundary is. And over that, on top, there is another adversarial setup where it's a single player game. Now it's not. So you're proposing instances, right? And for that instance, the adversarial setup at the bottom is trying to do the advantage location. And yeah, it's not
I'm
easy.
wondering, I guess what I want to say is also if you could build these estimators in a way that they don't only tell you for an instance the difficulty, but where you can also like use say it, well, I want to have a difficult one, so tell me the instance
Yeah. I mean,
or sample from instances.
I mean, imagine you have achieved with some amazing magic to create a very fast generator of instances that have advantage. And then you train an AI model on this distribution, and then it generates more.
Yeah, exactly like that. Yeah.
Maybe that's possible. I mean, we are doing a similar, not exactly this, but a similar project with a US team. There, what we are doing is we are sampling from spin configurations of a many-body state. And that many-body state is prepared after a long time evolution with some local, strongly correlated easing Hamiltonian, like the quantum dynamics slide that I flashed. Then all of these spin configurations are representations of that state, right? They're all classical snapshots, right? And then we train an AI model to learn them, what they look like, the distribution of them, and then ask for more samples. So that's like a surrogate of sampling from the quantum state without having prepared it. But you need to get the data to prepare this AI, you need a quantum computer in the first place, right? So I think it's similar vibe to what you're saying, but what you're saying is even harder because you have the extra constraint of queasiness, whereas in what I described, we have chosen exactly the regime of the Hamiltonian, where we know it's classically hard, right? And we're pushing the quantum simulation, so the quantum computer has advantage for that. But yeah, the motivation is similar.
Yeah, right. Cool. Other questions by the participants? Feel free to raise your hand or put them in the chat. This is your chance to talk to someone who's actually building exactly these kind of frameworks and running those kinds of experiments that I think were included in the announcement on Wednesday, or there will come more announcements based on this. Okay, but I don't see any for now. Then Konstantinos, thank you very much. So we will upload the recording to YouTube and also share it with all other participants again. And then I think Konstantinos, you will also actually be in Bradford in 2 weeks, no?
No.
Oh, you won't be there. Okay. Well,
No, I will be in Singapore.
Other duties. But yeah, some of your colleagues.
I will have Asian food in Singapore, not Asian food in Bradford.
Okay, yeah, that's a good way to describe it. Cool. Thank you so much, Konstantinos. Then also everyone enjoy the remaining of your Friday and have a good start into the weekend.
Yeah, thank you very much. Good to see you.
Thank you. Bye-bye.